So anyway, this is sort of, this equation is supposed to be the summary of what just happened, okay? So that's the main thing we want to focus on, is that this equation expresses the result of a division problem. And it says, you know, your 95 is 13/7 plus 4 left over. Okay, now in language you may have learned a long time ago, there's like words people use. We already said quotient and remainder. This number here is the dividend, the thing you're dividing into. And what we have over here is the divisor. That's the 7 times the quotient, which is the 13 plus the remainder, which is the 4. Okay. Now, the purpose of the thing we're about to see today is, this is a very misleading name. You guys learned the actual algorithm to do division when you were small children. Okay, we're not going to learn that here. What we're actually going to learn about is something that's a theorem related to this. Okay, it's not about how to do it, it's a theoretical result. So it's just, for whatever reason, people like to just call this theorem the division algorithm. So let me state it over here. All right, so the division algorithm goes like this as a statement. So you start with two numbers, which are a dividend and a divisor. So let's suppose A and B are integers. A is going to be the dividend, B is going to be the divisor. And what we're going to assume about the divisor is that it's, well, first of all, it's definitely not going to be 0, but we're going to assume it's positive as well. So let's suppose these are integers with B positive. Okay, and so what the statement is here is it's an existence and a uniqueness statement. So then there exist unique integers Q and R. And these are going to be quotient and remainder, which satisfy two things. So first is going to be an equation that looks like this thing right here. So the dividend can be expressed as the divisor times a quotient plus a remainder, like that. That's this equation. So it's always possible to do this. And something else that's important, one last thing in the statement over here. And it has to do with remainders. And the thing about remainders is, you know, like back up here, you don't stop when you have 25 left. Like you don't consider 25 to be the remainder. You keep going. But you stop when this thing's less than the divisor. So the last bit is that the remainder is supposed to satisfy that it's smaller than the divisor, and it's not negative, like that. Okay, so what this is, though, it's just a, as it says, it's an existence and a uniqueness statement. So it's asserting two things. First, Q and R exist, and second of all, they're unique. So, I mean, in terms of grade school problems, what this is saying is just simply that when someone hands you a division problem in grade school, there's an answer to the problem. Right? There's a quotient, there's a remainder. There is an answer to the problem, but there's only one answer to the problem. Like you can't get two different answers to the same division problem. Okay, so I mean that might not sound like it's not going to blow your mind or something, but it's actually an important sort of basic foundational result in number theory. That there'll be a lot of times in this course where working with objects in the middle of a proof, we're going to want to invoke this and basically like take a number and write it as a, you know, something times a quotient plus a remainder. And so it's not the most glamorous thing, but it actually is going to get used a lot. Okay. So anyway, where we are here is we just want to prove this. So we want to prove such a quotient and a remainder exists, and they are also unique. Okay, and so again, these existence and uniqueness type statements, you can think of them as asserting two separate things: the existence and the uniqueness. And in the context of proving such a thing, then you have to do two proofs, basically. You have to prove the existence and you have to prove the uniqueness. And those are usually done independent of each other. Okay, so it's two separate things to prove. So let's take a look. Okay, and so anyway, for the proof of existence, here's one way to look at it. Maybe just the inspiration is, you know, just think of it this way. Like pretend you had a calculator in front of you, and I gave you two big integers and asked you to find the quotient and the remainder. There's an easy enough way to find the quotient, which is, you had a calculator, you can divide them, and you might get the answer is like 31.1289 or something. What did you say, 31? Okay, 31, what, you get something like 31 point blah, blah, blah. You say, oh, well, 31 is the quotient, and then there's some remainder I could sort out. But that's essentially what you would do is you could divide them and just round down, basically, to the nearest integer. So in the context of a proof, you could do something like that, which is to say, let's let Q, Q is going to be the largest integer less than or equal to the actual quotient of A over B, which is not an integer necessarily, right? That's something that should be some rational number. Now, actually, I think I needed to step back a minute just to help orient you guys if you need it. So, so anyway, this is, as I mentioned to you, I believe, like we'll prove a lot of things in this class. Have you guys taken either, well, let me say it this way. Have you either taken like an intro to proofs class like Math 310 or maybe that CMSC one, or maybe just some math class where you were sort of beyond that proving? So do you want to give me a show of hands to just, so you kind of like, okay, so I mean, for many of you, you've probably dealt with this stuff a little bit. But anyway, what I wanted to just point out in the, as like a proof writing sort of comment is that what we're trying to do is an existence proof. Okay, so you're trying to prove something exists, and when you're actually trying to do this, usually what you do, not always, but often what you do is you have to actually like create the object, like produce the object. To show it exists, you have to say what it is, and then establish that it does what it's supposed to do. Okay, and so just to back up a second, that's what this first line is supposed to be. Like if I'm trying to tell you that a Q and an R exist, I have to kind of explain where they come from. Like how do you build them out of A and B, right? So, and that's what this first line is doing. It's explaining like how to build Q, or what the candidate for Q is going to be. It's going to be this thing, and in a moment I'll tell you what R ought to be. Okay, and then just saying what they ought to be is not enough for a proof. You have to then prove they do what the theorem claims they're supposed to do. Okay, so we're going to build them, then prove that they do what that thing says they're supposed to do, which is the last part on the bottom with the equation and the inequalities. Okay, so going on, what we get out of this is we just said Q is going to be an integer less than or equal to A over B. It's the biggest one that's like the closest to A over B. What that implies is that the next integer after Q would be larger than A over B. Like that. Okay, so we've arranged Q so that this is true, basically. That's the definition, more or less, for Q. Okay, now what this implies, if you were to manipulate this and multiply everything in sight by B, so this implies that if I multiply all expressions by B, which is positive, by the way, then B times Q is less than or equal to this thing times B, which is A, which is less than this thing times B, which is BQ plus B. And then what I just want to do to that is just take away this common B times Q from every expression. So if I subtract B times Q from everything in sight here, you end up with this. Right here. Now, the thing about A minus BQ is that should be the remainder. Right? That's what, if you think about what's supposed to be true, A minus BQ is supposed to be the remainder. And we've chosen Q so that this thing is in the sort of correct range of values that a remainder is supposed to be in, right? That's this over here. Remainders are supposed to be between 0 and b with inequalities like that. So this thing is really the r, so we're going to let r be this thing right here. So this is the other part of the proving this existence, and you have to say what q is, you have to say what r is. We already said what q is, now we'll say what r is. So we're going to let r be built out of a, b, and q in this way. Okay, so we already said what q is, so that expression makes sense. And this thing is r, and it's in the right range of values. Okay, so what's true then is that from what's above, we've already got it that says this. So from this previous thing. And so that's half of what we needed to prove, and then the other half is that A is supposed to equal BQ plus R. Okay, so what is BQ plus R? Just figure out what's going on with that. So BQ plus R is in fact BQ plus whatever R is, and R is this. Right, so if you evaluate BQ plus R, plug in the definition of R, you're looking at this expression, which is simply A. Okay, so that line is proving that BQ plus R is the same thing as A. That is, A is equal to BQ plus R. So we said what Q and R were. We established this fact and also that fact. And that's the two facts down below. So that's the completion of the existence proof. Okay, so its existence proof is done. We've shown they must exist. And then we just have to do the uniqueness part next. Okay, does this part make sense? Any questions? So that's the end of the existence proof. So then next you would do uniqueness, and it's kind of like it's an independent proof. Okay, you can do these in either order. You could whatever we're going to include here is not meant to be dependent on the previous proof. Okay, so anyway, just another general proving statements kind of comment here. If you're going to prove uniqueness, there's usually a standard approach that works pretty well that people like to do. So the sort of standard way to prove that something is unique in mathematics, it means there's only one of it, like you can't find two different ones, is to assume there's two different ones. So what you do in a proof like this, you assume there are two different ways to do this, and then you work to somehow prove that they're actually the same way. So you prove a statement that says, if I have two different ways to accomplish this thing over here, then in fact they must be the same way. And that makes it impossible for two different ways to exist. So the idea here is to suppose there are two ways to do it. So when I say ways to do it, I mean, suppose we have two different pairs of quotients and remainders that satisfy these conditions. So suppose there are two ways to do this. So what I mean by this is that we have, suppose we could write A as B times a certain quotient plus a certain remainder. And also, A is equal to B times a different quotient plus a different remainder. With that additional condition of remainders satisfied for both. So that 0 less than or equal to R1 less than B, and like that. Okay, so up front we're not assuming they're different. We're just saying suppose we were given two different ways to do it, and we're going to argue that they have to do the same way. Okay, so it's not really a proof by contradiction because we didn't pretend they were different. We just said we have two, which might be the same, and we'll prove they're the same. So what do? We just have to take what we're given and try to make some progress with it. So the first place to look to make some progress is to say that this and this are both equal to A, so they're equal to each other. Okay, so this thing right here and this thing right here, these have to be equal. Right? So we'll start with that. So we have, I'll just write it again. A is b cubed 1 plus r1, which equals ab cubed 2 plus r2. And then you can kind of, I'm sorry, b, I don't know what, it's just b cubed 2 plus r2. So you got that, and now you forget about a for a second and just use this equation about b, q's, and r's and try to do something with it. So, I mean, the one sensible thing to do here is to try to group the quotients on one side and the remainders on the other. Okay, so like you could write this as bq1 minus bq2. Like subtract this term from both sides, and then subtract the r1 from both sides. You have that. Okay, and now there's something about this, which if you think about it, what's going on with everything here, you start to realize there's something you can like latch onto in a second. So what's going on here on the left side of the equation, right, is I just factored a b out, right? That means it's a multiple of b, right? And we're almost always in this course working with integers. That's an integer multiple of b, right? So it could be like, could be b, could be 2b, could be 3b, stuff like that. Could be negative. But anyway, what's on the right is a difference of two remainders. And the remainders are kind of constrained in terms of how big they can be. Right? They're non-negative, but they're less than b. Right? So how could you take two things that are non-negative and less than b and subtract them and get a multiple of b? Right? Like, so like it's less than b. If you take something away, it's going to get even smaller. It could go negative, I suppose, but you're not taking something that large away. So if you think on this for a while, and we can prove this, but if you think on it for a while, like this difference of remainders can't actually be as large as b or as negative as minus b, which sort of leaves nowhere else for it to be except for 0 times b. Okay, and so that's essentially the idea. So what this shows, okay, so this shows, it shows that b divides the difference of remainders, first of all. The difference of remainders is a multiple of b. However, what's true, right, so we have, let's write it this way. We know this is true. That's this one, I just copied it down. What I would like to do is take this one and write it down, except I'm going to flip the signs of everything. So if you multiply everything in this one by minus 1, what you end up with is this. Okay, so those are two things that are true about our remainders. And I just set them up that way because what I essentially want to do is just add these inequalities and those inequalities together. And what you get. Because it was strict on both sides for one of them, it's going to be strict overall. But what happens is you add these things together, and on the right you get b minus 0, and on the left you have minus b, 0 plus minus b. So you end up with something like this. So you have the inequalities which show you that your difference of remainders is strictly between minus b and plus b, but we do know it's a multiple of b. It's an integer multiple of b. So it has no choice but to be 0 times b, essentially. Okay, so right, multiple of b. Okay, so what you conclude right here is that this difference of remainders has to be 0. There's nothing else it could be. Okay. So that's good news. Because we're almost done. That's good news because if the difference of remainders is 0, that actually tells you the remainders are equal. Okay. So this tells you R1 equals R2. That's the kind of thing you're trying to establish in the proof like this. You started out with two different ways. You want to show they're the same way. So the two pairs are the same. So we just showed that the two remainders are actually the same. And the only thing left to do is to show the two quotients are actually the same. So that's not a big problem because of this line up here. Maybe this had that b times the difference of quotients is the difference of remainders like that, which is 0. So b times q1 minus q2 is 0. And that's going to imply q1 minus q2 is 0. Something we're using here is that b is not 0. So you can divide both sides by kind of cancel off the 0. So anyway, that's it. That tells you the quotients. So again, that's uniqueness, right? Assume you have two different pairs that do the same job, and then you like show they're the same one all along. Okay. All right. What do you think? Okay. Okay. Again, this is not the most exciting thing, but it's kind of foundational to this whole subject. So again, the point is not to blur division, but just to get comfortable with this result, and we'll think about using it. There are a couple examples I just wanted to draw attention to. I mean, doing an example with this is kind of like doing division, which is, like I keep saying, not really the point. But there's some things to draw attention to. So here is one example, which is supposed to be straightforward. Right, so whenever you have an A and a B, you get a Q and an R. Again, it's all just about doing division, but if you want to just process a few examples, here's one. So this is like, well, if I had A is 100 and B is 9, and I wanted to see what happens when this division algorithm statement's invoked, it says we get a unique Q and an R, okay, but it's just the quotient and remainder. So the statements, or the way this would look, right, is you could take 100 and you could write it as what? I guess 11 nines, right? That gives you 99 plus 1. So in this case, Q is 11, R is 1. Okay, that's supposed to be a straightforward example of what's going on in this statement. A nice example to think about, because it was not excluded from this discussion, is that the dividend can be negative. So this is just something to pay a small amount of attention to. So no, in the statement, A could have been any integer. We did say B is positive, but A could have been any integer. So you could have something like this. Let's say I take A to be minus 10 and B to be 9, and I want to find the unique Q and R as in the division algorithm. What should they be? And you just take a little bit of note of what's going on here. But the dividend can be negative, but the statement about remainders was they are never negative. They are always non-negative. Okay? So what's going on here is, always really, is you need to find like the biggest multiple of the divisor that's less than or equal to your A. Okay? And minus 9 is not less than or equal to A. You need to go back another multiple. So you would actually want to think of this as negative 18 plus an 8. Okay, so in this case, the way it would look is you could write minus 10 as the divisor times a negative 2, and then plus a remainder of 8. Okay, so that's would be what's going on in this statement in the case of a negative. So just take note of that. It's not like not like the quotient's minus 1 and the remainder's minus 1 or something like that. This is the way it works out. So here Q is minus 2, R is 8. Okay, and so the last example is just to point out a very small thing that I think you all know. But if I had something like this, which is very straightforward to do division with, you can divide 42 by 7. It goes in evenly with a quotient of 6. So in terms of what we're talking about, 42 is 7 times 6 exactly. So it's like plus 0. Right, so anyway, that's would mean our Q is 6 and the R is 0. And I mean, of course, that's it's an example where the divisor divides evenly into the dividend. And just a small point to be made is that situation is characterized by the fact that there's zero remainder. Right? That's, so you have the divisor divides evenly into the dividend if and only if the remainder is zero. Okay, so let's just leave that as a little comment here. So B divides A if and only if the remainder R is equal to 0 when A is divided by B. Iterations. Write a better sentence. Yeah. Okay, and so this is something that it'll show up in a couple places down the line. There'll be a couple, maybe some proofs or something where we're trying to justify why some number divides another number. And sometimes the good way to go about doing that is to invoke the division algorithm to get the quotient and the remainder, and then in your argument prove the remainder is 0. And so there'll be a few places where we treat things that way. Okay. All right, so we okay? You guys have any concerns? All good so far, I hope. Okay, so we're going to move on to talk about greatest common divisors. Next, GCDs, as we will call them. So this is section 2.6 is called the greatest common divisor. Okay. Now, here's a fact that's true. Okay, so if you have a non-zero integer, so any non-zero integer has only finitely many divisors. Okay, so this is not going to blow your mind, but it's true. We mentioned something early on that if you have, let's say, a positive integer and a positive divisor, that the divisor cannot be larger than the thing it's the divisor of. Okay, we mentioned that fact, but that fact actually relies on the thing you're dividing into being non-zero. Okay, so this word is a little bit important here. The number 0 has infinitely many divisors. In fact, any integer divides into 0, let's say except 0 itself. So that's kind of an important word, but this is supposed to be a fact that doesn't bother you when you hear it. So what we're going to talk about, though, is say if we have a pair of integers, and what divisors do they have in common? Okay, and so let's say hence, if two integers, a and b, are not both 0, what happens then is the set of their common divisors is finite. And let me also just add and contains the number 1, because 1 divides everything. Okay, but anyway, each one has finitely many divisors, so they can't somehow have infinitely many divisors in common. That wouldn't make any sense. So anyway, when you have a finite set of numbers, it has the biggest thing in it. Okay, so what this means then is there is such a thing as a greatest common divisor. Okay, so therefore, they have a greatest common divisor. Which we shall denote GCD, parentheses A comma B, like that. Okay, and I mean, this is essentially the definition. I didn't want to be a little too formal, but I mean, the definition of greatest common divisor is the greatest element of the set of common divisors. That's what its name says it is, basically. Okay, but anyway, it will have such a thing. There's, and the number one's in here, so one is sort of the smallest it could be, right? One is a common divisor, so the GCD can never go lower than one. But in a lot of cases, it's larger than one. Okay. So that's what is meant by a greatest common divisor. We can just look at a couple examples that are ones with small numbers, just to make sure we are totally fine with this concept. So we're going to look at these, just some examples that we could just figure out because the numbers are small and we don't have to think too hard. But a little bit later, we'll have a nice algorithmic way to compute these things, like perhaps if we have really large numbers. So anyway, let's put a couple examples up. I mean, okay, look, so I want to make sure we understand the concept here. Okay, but anyway, look, the divisors of 6 are just what? 1, 2, 3, and 6. Okay, the divisors of 15, if you think about it, are 1, 3, 5, and 15. They have 1 and 3 in common. Those are the common divisors. So 3 would be the greatest. So I'm happy to just write that and hope you guys are okay with that. Okay. So GCD of 6 and 15 is 3. Just some other examples that are maybe sort of extremes in one way or another. Here's another one just to look at and see what happens. Now in this case, what you might notice about the pair of integers here is that 12 is in fact a divisor of 36, right? But any number also divides itself, right? So 12 divides 36 and 12 divides 12, so 12 is in fact the largest divisor of 12, so it's going to be the largest common divisor. And so you can kind of see what happens in such an example. If one number divides the other, like this, then the GCD will be that number, the divisor one. Okay, that makes sense? Here's a different example. Okay. Do you know what this one is? You can tell me. You can shout it out loud and proud. It's 1. It's 1. They have nothing in common in terms of divisors. I mean, the second one's only divisible by 1, 5, and 25, if you think about it. And those do not divide into 8. Well, 1 does, right? 1 divides into anything. So 1 is a common divisor, but they have no other common divisors. So this is a bit of an extreme example, right? It's like if that's as small as the GCD could have ever been. And that's what happened in that example. It was 1. Okay, one more example, just to make sure we get it right. What if we had the GCD of 24 and 0? Now, I was trying to make a big deal out of the number 0 over here, but there's something you might notice. I did say if A and B are not both 0, right? So I didn't say 1 couldn't be 0, but here they're not both 0, and that's okay. So 24 has only finitely many divisors, so there's only finitely many common divisors here. So there is a GCD. What is it? Yes, it's 24, right? Yes, very good. So this one is just to see that as an example of this type. So remember, everything divides 0. So 24 divides 24, and 24 also divides 0. So just remember. Right, A divides 0 for any, let's see, 0A. Okay, now what is not okay is the GCD of 0 and 0. Okay, so we won't speak of such a thing. I don't know, I'm speaking of it currently. But it doesn't really exist or make sense or something. Okay, let's say it doesn't make sense. I mean, formally speaking, right, 0 and 0 have a lot of common divisors. They do not have a greatest one because there's infinitely many larger and larger common divisors. So you might think we should just say infinity or something, but there's no reason to. And there's actually other reasons why people sometimes like to say the answer is 0 for some reason, which are probably mysterious, and that's okay. But it's a definition. Anyway, we don't need to talk about it. It's not going to come up in any meaningful way. Okay, just maybe be mindful of the fact that that doesn't make sense. So if you're okay. So anytime we talk about GCDs, it should be the case that they're not both 0, like this. All right. So hope the examples are okay. This example right here is worth building upon anyway. So this is an important kind of thing. It has a name, so we'll make a definition here. So 2 integers, A and B, are called relatively prime if it's true that their GCD is 1. Another word people use, you might have heard, is coprime. The book says relatively prime. I'll probably say that most of the time, but just so you know, those are the same concept. They mean the same thing. But anyway, things that are relatively prime, I mean, that's a relationship between 2 integers, right? And things that are relatively prime to each other do not need to be prime or anything like that. As you can see in this example, neither of those is a prime number. But there's a sense in which they're prime to each other. They have nothing in common with each other, so to speak. Okay, so anyway, as we can see over here, just for a quick example, what do we call them? 18 and 25. Right, so as an example, 18 and 25, they're relatively prime to each other. 6 and 15 are not. Neither are these. Sorry, neither is this pair nor that pair. Just one more thing. Maybe we can say one more thing, and it's probably enough. Actually, one extra thing I just want to insert on the side here is just note always. Said this out loud, but I just wanted to remind you that GCDs are always at least 1, so this is the extreme example, and it's as small as it could possibly be. Anyway, the other thing I just want to say is one more thing to ponder is, what about if one of your 2 integers is a prime? Right, so if you're taking the GCD of a prime with something else. So if well, I mean, a couple things can happen, but I want to think about something like this. Right, if I have a second integer n, and I'm thinking about the GCD of p with n, then in fact what can happen, I guess we'll say it this way, is there's 2 possibilities. Okay? I just want to point out that one of them being prime doesn't make things relatively prime necessarily. Right? So any common divisor of p and n has to be a divisor of p. P has 2 divisors, 1 and p. Right, so this can only ever be 1 or p. And I guess just to add one extra sentence underneath. Right, so they might be relatively prime. That's what would happen if it was 1. But if it turned out to be p, that would mean that p divided n. So n might end up being a multiple of p. So we'll say it this way: GCD of p with n is 1, if and only if p does not divide n. Okay, so keep that in mind just for now and in the future. Such GCDs don't have to be 1. There's a really great chance I'm going to fall on some lights, and this tile's sticking up on the trip. Okay. So, okay. let me know.